Welcome back to Digital Systems 2. In this video, we're going to go over MOS technology, low voltage technology, IC interfacing, and analog voltage comparators. So in the last video that you watched, you saw the discussion on TTL characteristics, which is just one family of logic devices. So today we're going to talk about MOS devices and CMOS devices, and then we're going to learn how we interface the two. So now that we have two different families, how can we make sure that those two different families will be able to work well together? And if not, what do we do about it? We're also going to talk about low voltage technology and comparators, analog voltage comparators. So first I'm going to quickly go over what MOS technology is. If you think about some of the examples that were shown in the last video, I mentioned that we were going to go a little bit deeper and show you what was behind the curtain when we think about the symbols that we see for the AND gate, the OR gate, the NOT gate, etc. So in the last video, we talked about the TTL family, which relies primarily on BJTs or transistors in order to wire each one of the logic functions that we generally use. Another type of technology relies on MOSFETs. MOSFETs are slightly different in how they are created, the materials that are used, and the way that they operate. We have two types of MOSFETs, an N channel and a P channel. You can think of a MOSFET in general terms the same way that you would think of a BJT. It's a switch. It allows current to flow from the drain to the source depending on the voltages that are applied. And we can control whether the switch is open or closed based off of that general idea. The name of the MOSFET comes from the fact that it uses MOS technology, that's metal electrode, over an oxide insulator, over a semiconductor substrate, and the transistors of MOS technology are considered field effect transistors. That's where the name MOSFET comes from. Notice that in our symbols here, we have the N channel and the P channel MOSFET, and the arrows are slightly different, showing a slightly different orientation in how they work, and I'll explain that in a second. So the N-channel MOSFET is a basic element in a family of devices known as NMOS. And if we look at the drain, the gate, and the source, here's the drain, here's the gate, here's the source. The drain is always biased positive relative to the source. So what does that mean? That basically means that the MOSFET will remain off, which means no current will flow from the drain to the source as long as the voltage applied from the gate to the source, we call that VGS, is below a predefined threshold, V sub T, threshold voltage. So if we want to turn the MOSFET on, we have to supply a voltage at the gate, from the gate to the source. That is, we have to supply a voltage from the gate to the source that is higher than a threshold voltage. Your threshold voltage might be 1 volt, might be 2 volts, it depends on the MOSFET, might be 0.3 volts, but in order to turn it on, I have to supply a voltage higher than the threshold. Once I supply a voltage higher than the threshold, it behaves similar to like a switch, where the switch will close and current will flow from the drain to the source. If current flows from the drain to the source, we then also have a voltage that is our output voltage. And that voltage is then carried through to the load connected to it. So when we have a MOSFET, we have two states basically, whenever the switch is open, whenever the switch is closed. If the switch is open, we have a really high level of resistance, 10 to the 10 ohms, which basically means you have next to no current flowing here, and we would say that the MOSFET is off. But if we were to have a voltage here, a gate to source voltage that causes the switch to close, then we have current flow, and the value of the resistance that you have when current is flowing is approximately 10 to the third ohms. So much less resistance, allowing current to flow. So again, it is helpful to think of a MOSFET as a switch that is either opened or closed between the source and the drain, and it's open or closed based off of the voltage that you supply at the gate. The P-channel MOSFET, or PMOS, operates in almost the same way as an N-channel MOSFET, with one small difference. The drain is connected to the lower side of the circuit, so it is biased with a more negative voltage relative to the source. What does that really mean? To turn on a P-channel MOSFET, you have to supply a voltage lower than the threshold to the source. To the gate. You have to supply a voltage at the gate that is lower or more negative than your threshold voltage in order to turn it on. So for example, if the threshold voltage for this particular P-channel MOSFET was 0.8 volts, I'd need to supply something, negative and lower than that value to turn it on. So here's sort of a summary of our P-channel and N-channel MOSFETs and how they work. Typically, the voltage you need from gate to source in order to turn it on is typically more negative than negative 1.5 volts, so maybe negative 4 volts or negative 5 volts, something more negative than that. With an N-channel MOSFET, you need a positive voltage, typically more than 1.5 volts in order to turn it on. Keep in mind that when the MOSFET is on, your typical resistance level from the drain to the source is about 1,000 ohms, and when it's off, it's about 10 to the 10 ohms. So PMOS and NMOS circuits began to dominate the LSI and VLSI markets in the 1970s and 1980s. If you don't know what LSI stands for, that means large scale integration and then very large scale integration. And during this time period, one of the main drivers of the electronics industry was the integration of more gates on a single chip. So large scale integration and very large scale integration refers to how we were able to increase our computing power, increase our data and our memory storage power by fitting more and more and more chips on a single gate. The smaller that we can make the gate, the more gates we can put on a single chip, etc. So we can use fewer components by getting more AND gates on a single chip, for example. And during this era, technology emerged that basically used PMOS and NMOS transistors in the same circuit, and this is called CMOS technology. So CMOS comes from the idea that PMOS and NMOS transistors were combined to create logic functions like AND or NOT, etc., on a single chip. Here's an example of the CMOS inverter. It has two MOSFETs that are connected in series. Notice you have one P-channel MOSFET and one N-channel MOSFET. And I'm going to just do a quick demonstration of how this creates an inverter. Here's our gate to source voltage being applied right here. This is your VCC that's being applied to the chip. Here's where we would take the output voltage right here. This is our truth table, which is going to help us to understand what's going on. And I'm going to just break this down very quickly. When Vin is high, keep in mind a high is 5 volts. When Vin is high, this MOSFET right here will be off because your gate to source voltage will not be below your threshold voltage. It won't be negative. And Q2 is on because this is an N-channel MOSFET. And when you apply 5 volts, that'll be well above your threshold voltage, and this transistor right here will be on. So now we can think about V out as being a simple voltage divider, where I'm taking the voltage across Q2 using a voltage divider. In order to use a voltage divider, I'd need to know the resistance values for Q1 and Q2, which I know. I can use this table here as a reference. So the voltage across Q2 would be the resistance for Q2 when Q2 is on, which would be 1K, divided by the resistance for Q1 when it's off, and the resistance of Q2 when it's on. Remember, when a MOSFET is off, it has a resistance of 10 to the 10 ohms. So my denominator of the voltage divider will be the sum of the resistance for Q2 when it's on, plus the resistance of Q1 when it's off. If I complete that voltage divider, I'm going to get a voltage that's next to nothing. showing that if I put a input voltage of high, I get an output voltage low. Now, if I look at the scenario where Vn is low, Q1 will be on and Q2 will be off. Q1 will be on because you'll have a gate to source voltage, which will be negative if you apply a low right here. The gate to the source, because this VDD right here is a positive 5 volts. So if you take the voltage from the gate to the source, that's 0 to your 5 volts. That's a negative bias. And so Q1 will be on, Q2 will be off. And if I complete a voltage divider once again, I have the voltage, the output voltage right here, which will be the resistance of Q2 when Q2 is off, which would be really, really high, divided by the resistance when Q1 is on, plus when Q2 is off, times 5 volts. You end up getting an output of 5 volts. So we can see that this is an inverter. When the input is high, the output is low. When the input is low, the output is high. And this is just one example of how a MOSFET implementation of an inverter works. Again, when you get to the semiconductors course, you will begin to study MOSFETs, BJTs, diodes, etc. in more detail. This is just a little sneak peek of what's going on behind the curtain when we have a CMOS device that is created to be an inverter. Here's a representation of a NAND gate using CMOS. Here's a NOR gate. So just some examples just to sort of get your mind thinking about the fact that the symbols you're used to seeing actually represent something else. They represent an electronic circuit that creates the truth table you know. And there's a whole lot of theory behind that that you'll learn in future courses. Now we're going to kind of switch gears a little bit and talk about low voltage technology. So IC manufacturers are continually looking for ways to put more semiconductor devices closer together on a chip. The closer together I can put them, the more I can fit on one chip. The more I can fit on one chip, the more versatile the applications of said chip. So increased chip density has some major benefits. It allows more circuits to be put on the chip, and with circuits that are closer together, the time for signals to propagate from one circuit to another will decrease. But there are some drawbacks. When circuits are closer together, the insulating material that isolates one circuit from another is narrower. And this decreases the amount of voltage that the device can stand before dielectric breakdown occurs, which basically is a breakdown of the materials that cause your circuit to operate the way it should. When chip power dissipation increases, this can raise the chip temperature above the maximum temperature you would want for reliable operation. And these drawbacks can be neutralized by operating the chip at lower voltage levels. So as we increase chip density and we have more gates per chip, it's a great way to expand the applications that we can do, but there is a cost to that. The cost is that you can't operate those chips at the same voltage level as other chips. So now we have the idea of low voltage technology. Low voltage technology basically means there is a family of chips. There's a family of chips that operate with lower voltages than we're used to. As a technician, this is something to be aware of. If you're in a laboratory and you find a random chip on the floor and you decide to test it or to use it in some way and are not aware that low voltage technology exists, you might plug that chip right into a breadboard, apply 5 volts to VCC, and immediately fry the chip. Because look at the VCC, the recommended VCC for these different part numbers. These are all low voltage technology part numbers, which means that you're never going to apply more than these ranges to VCC. And if you had a circuit where you had a mixture of chips that are typical regular voltage technology and low voltage technology, you would need to really make some considerations on how you would interface those two chips together. If you think about the output voltage for a high level and a low level, you really have to consider how that affects your circuit if one of your chips uses low voltage technology. Next, we're going to move on to a new topic called IC interfacing. Interfacing basically means connecting the outputs of one circuit or system to the inputs of another circuit or system. And when we discussed fan out in the last lecture, this was similar to the idea of interfacing. The simplest and most desirable interface between a driver and a load is a direct connection. So if you think about the examples we did in the last lecture, we had direct connection. We were considering the output of one NAND connected to the input of another. And often a direct connection cannot be made due to a difference in electrical characteristics. So in the examples that we did before, those examples are great, but in the real world, we may not be able to connect the output of a NAND directly to something else. Sometimes we'll need an interface. An interface circuit is connected between the driver and the load so that the output from the driver is conditioned or changed in some way so that it's compatible with the requirements of the load. And now that we're talking about two families, the TTL family and the CMOS family, now we have to really consider if the output of one chip is really going to be compatible as an input to something else. And this is where interfacing comes into play. So, imagine you have a driver. Imagine you have a load. An interface might be needed if the signal coming out of the driver is not going to be compatible with the signal that the load requires. So, when we consider whether we need an interface, we have to consider, are the highs high enough? Meaning, is the output voltage from our driver high enough that the load will interpret it as a high? And are the lows low enough? Meaning, is the output low from the driver low enough that the load will interpret it that way? We also want to consider that with a noise spike. And if we can say that yes, the highs are high enough and the lows are low enough, even with a noise spike, we don't need an interface. And this particular example would also assume that all your current loading, your current sourcing and syncing is acceptable as well. But let's say that your highs are not high enough. So the high coming out of a driver is not high enough for the load to interpret it as a high. Or let's say that your low is not low enough. In these cases, we would need to have an interface. We would need to insert something in between the output of the driver and the input of the load to condition that signal and make it so that the input can be interpreted the way the output is meant for it to be received. So we're going to consider two ideas: whether devices are voltage compatible and whether they are current compatible. So first, let's start with voltage compatible. So devices will be considered voltage compatible under these conditions right here. If the high level output voltage for the driver is larger than the high level input voltage for the load, plus a possible noise spike, no issue. Also, if the low level output voltage for the driver plus any potential noise spike is still low enough than the low level input voltage for the load, no issue. We call that voltage compatible. So we're going to be considering this idea when we compare a CMOS device to a TTL device. So now we have two different families. It's like shopping for bread at Publix and comparing that to the price of bread at Walmart or Winn-Dixie. They all have bread, but who's got the better price for your needs? Same idea. So now we're going to be comparing and contrasting two different families to make sure that they're compatible, to make sure that the output of one is either high enough or low enough to be the input for something else. If not, that's when you need an interface circuit. We also are going to consider whether devices are current compatible, and this is how we'll determine that. If the high level output current for the driver is bigger than the high level input current for the load. So think about the fact that the input current, the high level input current for the load is going to be a certain amount. The driver has to provide enough to drive that load. So that's why the high level output current needs to be higher than what the input is requiring. Just remember too, in the low state, we still have the idea of current sinking. So the low level output current for the driver needs to be bigger than what will be sunk by the low level input current coming from the load. So we're going to be comparing characteristics and determining whether an interface might be necessary between two different families. So let's take a look at some examples. First, we're going to compare the output voltages of a TTL device to the input voltages of a CMOS device. So imagine that the green box represents voltages from the driver. And in this case, the driver is outputting a high signal. The question is, are these highs high enough so that the load will interpret them as a high? So imagine that the load might be any one of these values. So for example, let's say that a 74 is going to be driving a 4000B. The 4000B needs a high level input voltage of at least 3.5 volts. This one's only going to provide 2.4. That's an issue. So your TTL device is going to be sending out a high, but your CMOS device won't be receiving it as a high because the voltage isn't high enough. So as we compare these output voltages in the high state, most of them, or all of them, are not high enough for most of the CMOS devices. Notice this one needs at least 3.85 volts, this one needs 3.5, this one needs 3.5. So we can see that these are going to be too low to interface or to connect with these part numbers. And that's a scenario where you would need an interface circuit to account for that. Here's an example of what an interface might look like. And this is an extremely simple example. But sometimes a pull-up resistor is used when a TTL device is driving a CMOS device. Here's what it would look like. Here's your TTL NAND gate. Here's your CMOS NAND gate. Normally the output would just be connected to an input, but in this case we add a pull-up resistor right here. And the presence of the pull-up resistor causes the TTL output to rise to approximately 5 volts in the high state, thereby providing an adequate CMOS input voltage level. So that resistor will cause these output voltages here to approximately double, being high enough that now each one of these part numbers will interpret that high signal as a high based off of its high level voltage requirements. This is one example of an interface circuit. There are many types. It all depends on your situation. But this is one small example of how we might have an interface circuit connected. Now we're going to take a look at CMOS being the driver and TTL being the load in the high state. So now let's assume that our CMOS part numbers are going to be driving a TTL load. And we're going to consider that the output state is currently high. So we're looking at the voltages that are supplied when the CMOS driver is providing an output voltage in the high state. So if we compare that to the load has a minimum voltage level requirement of 2 volts. And we can see that the driver in any case is going to provide more than that. So we wouldn't need an interface circuit if a CMOS was driving a TTL device in the high state. No issues here. Now let's look at current. So if we look at the high level output current for a CMOS device and compare that to the high level input current for a TTL device, we can see that here's the current that would be supplied. Here's the current that would be required. In all of these cases, no issues. But the 74 is listed as needing 40 amps of current, which is extremely high. That's extremely high. This may even be a typo. So I'm going to investigate that, but it is what's listed in your book. So we're going to go with what's in the book for now. But if this is true, and the 74 requires 40 amps, then none of these part numbers would be able to supply that high level of current, and you would have an interfacing issue. Again, this is a maximum value. This could just be a worst case scenario value, and in actuality, the typical value is most likely much lower than this. But since it's how it's printed in the book, we will go with it for now. So let's look at CMOS driving a TTL device in the low state and consider noise margins. So we're going to remember, this is right here. This is what we're going to consider for voltage compatibility. Voltage compatibility. So in the low state, we want to consider if the low level output voltage plus your low level noise spike is less than your low level input voltage. If it is, you have no issues. So we're going to look at the driver. We're going to look at the low level current for the driver and the low level noise spike. And we're going to add these two values together for each part number. Add them together. So for example, 0.05 plus 1.45, this is for the 4000B, is clearly too high for the 74 part number. The 74 part number can only accept a maximum of 0.8 volts if this input is going to be considered a low. The 4000B is going to send way more than that. It's going to send like 1.5 volts. Way too high. That's a case where an interface may not be needed. I mean, where an interface will definitely be needed. Sorry, an interface will definitely be needed. Look at some of the other scenarios, and we can see that maybe right here, here's a scenario where the low level output voltage is 0.1 volts with a possible noise spike. That would be 0.8 volts, and that would be enough to satisfy this requirement here. So it depends on your part numbers. Some part numbers are going to be voltage compatible and some are not. So you would have to compare your specific part numbers to know if a specific circuit is going to be voltage or current compatible. So we're going to look at an example of current, again, in the low state. Just a reminder that in the low state, and as the CMOS output is just like the TTL output, it acts as a current sink. So I put this in here just to remind you, when we think about current flow in the low state, we have to think about it sinking current, meaning that current will flow back into your output. So now let's look at the CMOS driving a TTL device in the low state, and we're going to look at current compatibility in the low state. And again, that means we're sinking current, and we have to look at the load and determine if the load is going to sink more current than the driver can handle. So look at our TTL, low-level input currents. If we compare those to our CMOS low-level output currents, see if you can identify an issue. One issue might be that the 74, the 74AS, the 74F, all of these are going to sink more current than the 4000B can handle. Can only handle 0.4 milliamps. So if this is my driver, this is my load, and I'm in the low state, 1.6 milliamps will be synced back here to this 0.4 milliamp. It's too high. So you would need an interface to deal with that kind of scenario. So as we think about who's driving what and then what state we're in, we're going to consider whether the driver and the load are voltage compatible and current compatible based on these this concept here as well as this concept here. And this is how we're going to determine whether something needs an interface. If it's not current compatible, if it's not voltage compatible, an interface would be required. So now we're going to see through an example how we would determine whether something is voltage and current compatible. So a 74HC output is driving 3 7406 inputs. Is this a good design? That's the question. Is this a good design? So we're going to start with considering a few questions. Begin with the state, either the high state or the low state. We're going to start with the high state, and we're going to ask ourselves two questions. Can the 74HC output provide enough voltage in the high level output voltage for the 7406 high level input voltage, even with a noise spike? And can the 74HC output provide the appropriate level of high level output current for the 7406 high level input current? So these are like the two questions we're trying to consider. And here's how we're going to do that. Our 74HC high level output is right here. So what I'm looking at is this piece of my voltage compatibility equation. We're going to see if this number, this 4.9, is larger than our high level input voltage for our 7406 is right there, plus our noise spike right there. So if I add those two things up, 2.0 plus 0.4 is 2.4. Is that less than our high level output voltage? Yes, it is. So when I'm checking voltage compatibility, it's voltage compatible in the high state. No issues there. Next, we're going to look at current compatibility in the high state. So I'm going to be looking at the high level output current of the driver. High level output current of the driver. Is that bigger than the high level output current of the load? In this case, I see an issue. If this 74 really needs 40 amps of current, I'm not going to be able to supply that from the 74HC. It's not going to be enough. That's a potential issue where an interface might be needed. But that's only half of the equation. We only considered the high state. Now we got to go back and do the same thing for the low state. And we have two questions, once again. Can the 74HC output adequate low-level output voltage for the 7406 low-level input voltage, considering noise spikes? And can the 74HC low-level output current sink current from the 7406 without damage? Consider that there are 3 7406 inputs, and remember that the 74HC will sink current in the low state. So now we have to consider that idea of sinking current and not sourcing current like when the state is high. Let's start with the voltage. So now I'm going to be looking at this equation right here. So I'm going to look at the low-level output voltage, for my driver, plus the low-level noise spike for the driver. I'm going to add those up and make sure that they are less than the low-level input voltage for the load. So what this means is if the low-level output voltage is 0.1, but there's a noise spike of 0.9, giving me a voltage of 1.0, is that going to be low enough that my load will consider that as a low? No, it's not low enough. It's too high. I can't supply more than 0.8 volts here. And if there's a noise spike, I will definitely go over that limit. So that's a second issue we've now identified. 2 issues so far. So that was considering the voltage compatibility in the low state. Now let's consider the the current compatibility in the low state. So we're going to be looking at our low-level output current for the load. For the driver, the low-level output current for the driver, which is here, and the low-level input current for the load. Keep in mind, we have 3 7406 inputs. So we have 3 times 1.6 milliamps. That will be sunk back to our CMOS driver in the low state. That's our third issue. 3 times 1.6 is going to be higher than 4 milliamps. That's going to be too much current. So our solution is this is not a good design. The 74HC00 can sink 4 milliamps in the low state, but the 7406 input is going to sink 1.6 times 3, which is 4.8 milliamps. That's too much. It's going to sink too much current in the low state. If there's a noise spike in the low state, we consider this in green, then our low level input voltage will be too high. We also considered the fact that our high level output current could potentially be too low for the high level input current. So there were 3 issues that we discovered by asking ourselves these 4 questions. So basically it failed 3 out of the 4 questions on this test. And this is how we want to think about interfacing. So because we could not say that this particular orientation is both voltage and current compatible in the low state and the high state, an interface circuit would be needed. Let's do another example similar to the one that we've done before. Now we have a 4000B output that is driving 3 74LS inputs. So we have 3. And our part number now is the 4000B, which is the CMOS. That's the driver. And the load is the 74LS. We have 3 74LS inputs. Is this a well-designed circuit? We're going to consider the same questions as before. We're going to look at the high state and the low state and ask ourselves the same 4 questions. Basically, in the high state, is the output voltage high enough, even with a voltage spike, a noise spike? Is the output current high enough? That's the questions we're asking. So let's take a look at the answers to those 2 questions for the high state. The 74LS has a high level input voltage of 2 volts. If there's a noise spike, it would have to have a high level input voltage of 2.7 volts. And this is going to, the driver is going to output a voltage of 4.9 volts. So that's definitely going to be high enough, even if a noise spike changes this requirement from 2 to 2.7. No issues. So that's fine. If we look at the current, keep in mind that the 4000B is going to be sourcing 0.4 milliamps, and the 74LS requires 20 micro. There are 3 inputs, so 20 times 3 would be 60 micro. This is definitely going to supply enough current for those 3 inputs in the high state. So no issues in the high state. It is voltage and current compatible in the high state. Next, we're going to consider the low state. And the questions we're going to ask ourselves are, can the 4000B output provide an adequate low-level output voltage for the 74LS low-level input voltage? Consider the noise spikes. And then again, we're going to consider the idea that the 4000B must be able to sink all of the current that will be supplied by the load in the low state. So let's take a look at the answers to these 2 questions. When it comes to voltage compatibility, we can see that the 4000B will have a low-level output voltage of 0.05 volts, but with a noise spike, that could get as high as 1.5 volts, which is going to be too high for the low-level maximum voltage for your load. So that's definitely an issue. Also, take a look at the current. The 74LS is going to sink 0.4 milliamps times 3. And that would be 1.2 milliamps, but the 4000B can only accept 0.4 milliamps. So we have another issue here. The solution here is that this is not a good design. In the low state, we can see that the 4000B can sink only 0.4 milliamps, but 1.2 milliamps will be supplied. We also can see that with a noise spike, the low-level output voltage would be too high for the low-level input voltage of the load. Our last topic in this lecture is the analog voltage comparator. It's a very useful device for interfacing digital systems and analog systems. So the comparator compares 2 voltages, and these could be analog voltages, not digital signals like a 0 or a 1. It could be 2 analog voltages. And basically what happens is, if the positive input voltage is greater than the negative, check out these two terminals here, the output is high. And if the negative input voltage is greater than the positive input voltage, the output is low. The comparator inputs can be thought of as analog, 3.5 volts, 2.4 volts, 6.7 volts. You can supply a range of input voltages that are analog, but the output is what will be digital, either high or low, depending on which input was bigger. The comparator is often referred to as a 1-bit analog to digital converter. So now we're just going to look at a quick design example where we might use something like an analog voltage comparator. Suppose that an incubator must have an emergency alarm to warn if the temperature exceeds a dangerous level. The temperature measuring device is an LM34, that's the part number. It will measure the temperature and puts out a voltage directly proportional to the temperature. The output voltage goes up 10 millivolts per degree Fahrenheit. So again, this is a temperature measuring device. It will output a voltage directly proportional to the temperature. The output voltage goes up by 10 millivolts for each degree Fahrenheit. The digital system alarm must sound when the temperature exceeds 100 degrees Fahrenheit. We're going to design a circuit to interface the temperature sensor to the digital circuit. We're going to use an analog voltage comparator to do that. So, first part of the equation is we need to compare the voltage from the sensor with a fixed threshold voltage. So ideally what we need to do is take the output of the sensor and try to determine if the temperature is too high based off of the sensor's output. If it is, we sound the alarm. That's our game plan. So first, in order to answer the first question, we have to calculate the proper threshold voltage. We want the comparator to have an output of high when the temperature exceeds 100 degrees Fahrenheit. So our temperature sensor is going to give an output that's 10 millivolts per degree Fahrenheit. So if the temperature is 100 degrees, our temperature sensor is going to be providing 1 volt as an output signal. So we need a way to sound the alarm if our LM34 is giving us higher than that 1 volt. If the temperature is higher than 100 degrees, we need to sound an alarm. The temperature sensor is going to sense the temperature in the room and provide a voltage level, 10 millivolts per degree Fahrenheit. So when the temperature gets to be 100 degrees, our temperature sensor is going to give us a 1 volt output. Here's approximately what our circuit's going to look like. Our temperature sensor is going to sense the temperature in the room and give us a voltage output, 10 millivolts per degree Fahrenheit that it senses. So we need to compare that 1 volt signal to something else, so that if that 1 volt signal goes any higher than 1 volt, we can sound an alarm. Here's our analog voltage comparator. It's going to compare the signal from the temperature sensor to a constant value. And whenever this signal gets higher than this one, a 1 will come out of here, alarm will sound. So we need to compare the output from the temperature sensor to a 1 volt signal. Now let's say that this is a digital circuit and we don't have a 1 volt signal. We only have the 5 volt signal coming from our board. How can we create a 1 volt signal to be supplied right here at the second input? So we need to set the negative pin of the comparator to 1 volt, and we're going to connect the LM34 to the positive input. In order to create a 1 volt reference voltage, we could use a voltage divider. Quick reminder, a voltage divider is used for resistors in series. Let's say that we have 2 resistors in series. We're going to connect the first resistor R1 to 5 volts, and we have R1 and R2, and then we have ground. How can we divide the voltage so that we get just 1 volt across one of these resistors? Here's our basic formula for a voltage divider. Your voltage across, I just put Rx, it's the resistor in question. So the voltage across whatever resistor you're looking at is equal to the resistance of that resistor divided by the total resistance in series multiplied by your input voltage. In this case, what we want to do is take this 5 volts and divide it so that we get a 1 volt signal across R2. This is R1 up here, and this is R2 here. I want to create a voltage divider that'll give me a 1 volt signal across R2. So, in order to do that, I'd have to have 1 volt equals the resistance of R2 divided by R1 plus R2 times the 5 volts going in. Now, if you do some algebra, you can manipulate this and discover that R1 has to be 4 times bigger than R2. As long as R1 is 4 times bigger than R2, you'll have a voltage divider where 1 volt is the output voltage. So let's just say I pick 2K and 8K. Now I could pick anything as long as R2 times 4 equals R1. In this case, 2K and 8K is what we pick. That'll create the voltage divider with 1 volt seen across R2. And what we're going to do then is connect that output to the negative terminal of your analog voltage comparator. At that point, we now have created a system that will be able to take the output from the temperature sensor, determine if the temperature is too high by comparing that to 1 volt. If it is, a 1 will come out of here and your alarm will sound. This is how we could use an analog voltage comparator to compare some analog quantities and then take a digital output to sound an alarm. So analog voltage comparators are very similar to analog to digital comparators, which we'll cover at the end of the course and we'll do a lab on at the end of the course. This is just sort of one kind of idea related to taking an analog signal and converting that to a digital output. And we'll be able to go deeper into that idea a little bit later into the semester. And that is the end of this video.